We'll close out this section with a method of differentiation called logarithmic differentiation. This is going to be a nice technique to use in three different situations. One, when you're given something that's particularly messy with lots of factors in a quotient or product. We can actually avoid the quotient and product rule oftentimes if we just use logs. Another time when it's not even just kind of nice to use, but just essentially required to use, is when we have an exponential expression where both the base and the exponent are variables. As far as I know, the only way you can solve the derivative of those functions is using logarithmic differentiation. And then finally, if it tells you to use logarithmic differentiation, that's when you know you're going to use it as well. So what the heck is logarithmic differentiation? Well, the technique is to take the log of both sides of the equation before you take the derivative. And then you'll try to simplify things using properties of logs and see where it takes you. So let's see. I certainly would not want to try to take this derivative without using logs, because you've got a messy thing raised to the 1/2 power. So the first step would be the power rule. Bring the 1/2 out front, drop this down to a negative 1/2, then take the derivative of the inside. The inside is a quotient, but in the numerator of the quotient there's a product. Oh my goodness. No way, Jose. I'm not going to do that without logs. So the first step here is to take the log of both sides. Use the natural log always in calculus unless there's some compelling reason not to. So we'll take the natural log of the square root of the fraction x minus 1 times x plus 3 squared over x minus 4 cubed. Okay, and the whole point is, while the left side gets a little bit more complicated, the right side gets a lot less complicated because we can expand this out using properties of logs. There's 1/2 of everything, right? Because everything is in the square root, so we'll put parentheses here. And then we'll take the natural log of x minus 1. That's positive because it's in the numerator. The 2 comes out front. It's a positive 2 because it's in the numerator. And we get natural log of x plus 3. And then finally on the bottom, we've got a negative. So 3 is going to be a negative natural log of x minus 4. All right, so that is definitely way easier to take the derivative of. So let's see if I can make a little bit of space here. Yeah, I'm not working with a whole lot of space. So let me shrink this down a bit, and I'll zoom in. All right, so at this point I haven't taken the derivative, right? I've only taken the log of both sides. It's an equation, so I'm allowed to do that. And then I've used properties of logs to expand this. Now it's time to take the derivative. I'm going to take the derivative of this with respect to x because it tells you to take the derivative with respect to x. So when I take the derivative of the natural log of y, I'm going to get 1 over y times dy dx. That's the chain rule, right? So this is implicit differentiation because we've got not y solved for, but something more complicated than y. The 1/2 sticks around. It's a scalar constant. Inside the parentheses, we get 1 over x minus 1. We get 2 over x plus 3. We get minus 3 over x minus 4. That was really, really quick. Now, pay attention to what you're trying to find. You're trying to find dy dx. So I haven't solved for dy dx yet. I'm going to have to get rid of this fraction. In other words, I'm going to multiply both sides of the equation by y. So that means that dy dx equals y over 2 times 1 over x minus 1 plus 2 over x plus 3 minus 3 over x minus 4. Now, I would contend that this is probably the easiest form of the final answer. You certainly could spend some time finding a common denominator and distributing things out and combining like terms, and that would not be wrong, but I don't know if that would be worth much. It would take a while, and you'd get a more complicated looking answer. I suppose if you had to set this equal to 0, then maybe that would be useful, but as it is, I don't think so. I think I'm going to leave it like this. The other thing we could do is instead of leaving y in our answer, we could substitute this massive fraction back into here. And that's fine. You can do that. But I don't feel like it, so I'm not going to. I don't want to rewrite that whole thing again. So as long as we know what y equals somewhere else in the problem, then it's probably okay to leave the y in your answer, unless the instructions explicitly said, write dy dx in terms of x only. And then you would have to substitute that back in. All right, this next one, we don't even know how to take the derivative of e to the x. So what is that even doing here? Well, we'll get there pretty soon, but we're not quite there yet. But let's try logarithmic differentiation. We're going to take the log of the left side, and we'll get natural log of y. We're going to take the log of the right side, and this is a fraction. So I'm going to have the natural log of e to the x plus 4 times the natural log of x squared plus 2 minus 3/2 natural log of x plus 1. And then also minus, because it's also in the denominator, 2 times x squared plus 3. Whoops, natural log. I was like, that doesn't seem right. 2 times the natural log of x squared plus 3. X squared plus 3. All right. So I kind of went through that part a little bit faster this time, but I'm, again, applying the properties of logs by taking the natural log of this side, taking the natural log of that side, and expanding out this mess. So once again, we get 1 over y times dy dx on the right side, on the left side rather, when we differentiate. So I'm going to try to keep this consistent and switch colors. When I take the derivative with respect to x of this equation, we got 1 over y times dy dx, as I already said. And now we got to deal with this natural log of e to the x. Well, I think we know what the natural log of e to the x is. Natural log of e to the x is just equal to x, because remember we're asking what can we raise e to, right? There's a base e here. What can we raise e to get e to the x? Clearly that answer is x. So this is x. So does that mean I put an x here? No, we put a 1 here because we're taking the derivative of x with respect to x, and we're going to get 1. All right, so now we get 4 times the derivative of the natural log of x squared plus 2. So the x squared plus 2 goes in the denominator. The 2x goes in the numerator. Don't forget that chain rule. It didn't show up in the last problem because all of them were just linear. Or actually, not just linear, but degree, leading coefficient 1 and linear. So the derivative was always 1. Like it is on this one. So we can do 3/2 times 1 over x plus 1, and minus 2 times, well, the x squared plus 3 goes on the bottom, and the 2x goes on the top, and that's done with the differentiation. Now we're just going to try to solve for dy dx and clean it up just a little bit. Again, I'm not going to bother rewriting the entire original equation. I'm just going to leave y in my answer. So multiply both sides by y, and then I've got 1 plus 8x over x squared plus 2 minus 3 over 2 times x plus 1 minus 4x over x squared plus 3. And again, if you wanted to, you could get a common denominator here, but I don't want to. So I'm just going to leave this as my final answer. Hooray. All right. So that leaves 2 more problems here, and these are both you can't really see one of those. Let's see. Scroll over here. These are both variable expression raised to a variable expression. So while we theoretically could have done this problem without logarithmic differentiation, we definitely can't do this one without logarithmic differentiation. We need to get those exponents out of those variables out of the exponent if we're going to have any hope of doing this problem. So in order to find dy dx, we're going to use natural log logarithmic differentiation. Remember that just means we're going to pull that x out front. So we've got x times the natural log of x. So unfortunately, we still have to do the product rule because this is a product of variable expressions, but at least we know how to do that. We didn't really know how to do exponential variable expressions. So yeah, so we'll switch our color to our derivative color, and we'll take the derivative of this equation with respect to x. Derivative of the natural log of y, I think we've done this before. Sounds familiar. I've done it every single time in these problems. Over here, the product rule tells you to take u prime times v plus u v prime. Actually, I think this is a problem that we saw earlier, right? It was y equals this, not natural log of y equals this. But yeah, this looks familiar. So we can solve for dy dx by saying this is y times 1 times natural log of x plus x times 1 over x, or just 1. And if you feel like it, since this is a pretty easy thing to write, it might be nice to write this as x to the x times natural log of x plus 1. And that should be your final answer. And this wacky function over here, sine of x raised to the cosine of x, same idea. We'll take the natural log of both sides. That cosine of x is going to come out front. We get the natural log of the sine of x. So when we take the derivative with respect to x, this 1 over y dy dx once again shows up. And we once again have a product rule problem. So u prime v, so u prime, oops, u prime is negative sine of x. V is natural log of the sine of x. Plus u times v prime. Well, v prime is the derivative of the natural log of sine of x. So put sine of x on the bottom, put the derivative of the sine of x on the top, and if you feel like rewriting this as cotangent, you can. If you want to write it as cosine squared over sine, then you can. Whatever you like. I kind of like getting rid of the fractions, I guess. So I guess I'll write this as a final answer of, I'll multiply the y back over to the other side. It is the sine of x raised, whoops, sine of x raised to the cosine of x. That's the y that I just multiplied to the other side. And then we've got negative sine of x times the natural log of the sine of x. This is a weird problem, isn't it? And then plus, again, since I'm going to try to get rid of fractions, I'll just write this as cosine of x times cotangent of x. But that's not the only way you can write it. Any equivalent form, in fact, even leaving it like this would be acceptable. But that's a good final answer. Ooh, crossing diagonally with my highlighter. Yay! And that is logarithmic differentiation. Fun stuff.